That's okay. Sorry, I mean, I was in a restroom. Okay, for a little bit longer. Okay, so let's continue our discussion on the MLP. Okay, so it's time to talk about like how Keras can be used to construct MLP. Okay. So as an example, we will start from a very simple image classifier. Okay, so in the earlier version of this textbook, okay, it used like a MNIST, which is like a handwritten digit images, okay, for classification. But here we are going to, in the second version of this textbook, we are going to use the fashion MNIST, which is kind of similar to original MNIST, okay, in the sense that it is also like 28 by 28 pixels, small images, okay, and it's also grayscale, and the size of the data set is similar, and it also has 10 different classes, okay, but as you can see from the name of this data set, okay, it's about like a fashion goods, okay, so you have like shoes, high heels, and pants, like a t-shirt, those type of like different dressing like items, okay, so and also the reason to replace the MIC with the fashion MIC is that this fashion MIC is a slightly more difficult classification task than the fashion MIC, because so then the MNIST, because the MNIST, original MNIST, if you use like a linear model, it already reached like 92% accuracy, okay. But if you use the linear model, the same linear model for this fashion MNIST, you only get like get you like 83% accuracy. So first, of course, we need to load the data set. Okay, so we load it by using Keras.datasets.fashion MNIST. This is provided as like a by the Keras. Okay, so you have like you get the X trend full, Y trend full, X test, and Y test. Okay, so you load it by using the Keras, not by scikit-learn. So difference is that every image is represented by 28 by 28 array. So it's 2-dimensional array rather than a 1D array of size 784. Okay. So the pixel intensity are represented as an integer, okay, from 0 to 255, rather than the float. Okay. So you can see like the shape of the data type. Okay, so X trend full shape. I mean, the shape, it has like 60,000. So we have 60,000 images, and the dimension is 28 by 28 for each image. And the data type is the unsigned integer, as we say, like it's because it represents the intensity from 0 to 255 integer. So we have like a training set, we have a test set, but we don't have a validation set. So we are going to, pretty much use like a 5,000 from the training set to be the validation set. And also we so we are going to divide the intensity by 255 to make it like in the range of 0 to 1. So that's like what happens in the next 2 lines. And then the fashion MIST has like 10 different classes. So here we try to list their class names just to get to give you an idea of what they look like. I mean, the first type is t-shirt, top, and then trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, ankle boot. Okay. So, for example, the first image in the training set represents a code. So you can use a class name ytrend0, okay, to see like what class it belongs to. So it's code. Here we list like the first couple of images from this fashion MIST training set. As you can see, the first one is a code, right? And here we have about the first 30 instances from the training set. Okay, just to give you an idea what the fashion MIST data set looks like. Okay, so even though each image only has 28 by 28 pixel, I think it's it represents, I mean, the item pretty well, right? So now, the first API that we would like to talk about, okay, is a sequential API. Okay, so you can use Keras sequential API to create a MLP model like this. Model equal to Keras models sequential. So you first create a model object, and then you call the add function method. Add method to add like for example, the first layer, which is the pretty much input layer. We call it flattened layer because we try to make the 2-dimensional data set into like a 1-dimensional. So it's flattened. Okay, so input shape is 2828. But after this layer, I mean, it's going to be 1-dimensional. Okay, and then we add chaos layers that dense. Okay, this is like the first hidden layer. We have 300 hidden 300 neurons in this layer. And activation is rerule. We set it to be rerule. And then we add another hidden layer as a dense layer, and we put 100 neurons there. Activation is rerule. And the last layer is output layer. Remember, this is a classification task, right? And we have 10 classes. So we have 10 neurons, and we set activation function to be softmax because it's a multi-class classification. Okay, so I think this is pretty straightforward. So I will not skip. Okay. So this, I mean, I already went through all this, so I will just. So alternatively, okay, you can use the sequential API like this. Okay. So model equal to Keras, not models, that's sequential. Okay, inside Okay, when you create this object, you directly provide the information for each layer, okay, in the constructor of this object, okay? So it is pretty much equivalent to the previous version of code, okay? It depends on how you like you prefer, okay? You can create an object first and then add those layers later, or you can create an object at the same time, provide the information for each layer, okay? And so this is like just to show you like how you can, you know, for example, if you write your name, write your import slightly differently, you may be able to save some words. Okay, for example, like if you say from Keras.layer, Keras.layers import dense, then you only need to call, you only need to provide dense, and the Keras knows like you are calling the Keras.layers.dense. Okay. You can also change the import, like from TensorFlow.Keras.layers to be like import dense. Then it works like this, or simply use the full path like this. Okay. The textbook used the last one, okay, because this is more detailed, okay, to be more clear. It will look more clear, but of course it depends on your programming preference. Okay, basically they are equivalent. Okay, and this, okay, you can use model.summary to list like the detail of your model. So you can see that here we have like flatten the first input layer. We have first dense layer, the second dense layer, and last layer, which is output layer. Okay, and their corresponding number of neurons. And for each of them, the number of parameters. Okay, so for example, the 235,500. Okay, the reason we have this many is because, okay, we have this each of these dense layer, neuron in the dense layer, in the first dense layer, okay, is connected to all these 784 input neuron. Okay, so it's going to be 784 times 300. Okay, and also we need to plus the bias term. Okay, bias term, which is I believe it's like because we have 300 neuron, so we have 300 bias. So all these weights, I'm sorry. Okay, we have all these weights, so they are here. And for this like 100 neuron dense layer, because it's 300 times 100 plus the 100 bias, so it's going to be, well, 30,100 weights and so on. Okay, and you can see the total number of parameter will be 266,610, and all these parameters are trainable. You may wonder, in what situation you have non-trainable parameters? We will talk about those situations at a later time, okay? But in general, when you create a model, most of the parameters are trainable, okay? The non-trainable parameters happens in the transfer learning situation, okay, in which you may want to freeze some parameters that we are going to talk about like at a later stage of this class, okay? So Sorry, I need like 1 minute to take the medicine. Okay. So I already told you like for density we have it can have like a lot of parameters. Okay, so that is also a reason. Okay, remember I told you like the neural network is very easy to get overfitting because we have so many parameters out there. Okay, but anyway, that's just want you to be aware. Okay, of this, and also you can fetch a particular layer. Okay, by the index. Okay, for example, here you list like you use model.layers and it will list all the layers for you and their corresponding memory locations. Okay, and then you can list like a specific layer. Okay, it will tell you like you can give the provide you can ask for a name. You can ask for like this layer is a hidden layer or not. Okay, so it's a a lot of there are a lot of operations you can you can do, okay, to each layer, and you can even get like a weights and set weights individually. Okay, so so here, okay, for example, okay, remember we are able to access like the first hidden layer, right? So we can we can use get weights to get the weights and bias of the first hidden layer and put it in the weights and biases. Okay, and then we can list all those weights. Of course, we have a lot of them. Okay, so just this is not like an exhaustive list. Okay, and the weights that shape. Okay, so we have like 784, 300. Okay, and the biases we have 300 biases. Okay, and bias shape is 300. So that's it. And then okay, because we didn't specify the initialization scheme. Okay, by default, okay, it is going to use a random initialization. Okay, there are many different initializers. Okay, that you could use. Okay, to initialize all these weights. Remember, we talked about like these weights had better to be randomly initialized, and we are going to discuss like different initialization techniques. But if you want to check out like what weight initialization techniques out there, you can check out the Keras.io initializers. Okay, and to learn like all the list of all the initializers. Okay. So the shape of the weight matrix, okay, depends on the number of input, obviously. Okay, so it is recommended to specify the input shape when creating your first layer. Okay, when you are using the sequential API. Okay, but if you do not want to specify the input shape, okay, that's fine. Keras will wait until it knows the input shape, okay, before it actually builds the model. Okay, so this is like this will happen, okay, either when you feed the model the actual data, okay, or when you call its build method. Okay, so but in most of the cases, okay, it's you know, it's better that you provide like input shapes for your model. If you don't have like if you didn't provide the input the shape of the input layer, then you will not be able to use the model summary, because, well, the Keras doesn't know like the shape of the model anyway. Okay. And once you have the model created, okay, you can compile your model. Okay, model by calling the model compile method. Okay, and here, okay, you can provide a loss function. Okay, for classification, normally it's a sparse categorical cross entropy. I will explain what it is later. And the optimizer is SGD. SGD stands for the stochastic gradient descent. I already discussed what that is, right? And matrix is accuracy. Okay, we want to optimize on we want to show the accuracy, okay, when you train the model. Okay, so what is sparse categorical cross entropy? Okay, it is equivalent of using loss equal to Keras dot losses sparse categorical cross entropy. So I already explained like SGD. So it is equivalent to like a specify optimizer equal to Keras dot optimizers dot capital SGD. Okay, and the matrix accuracy is equivalent to matrix equal to this one. Okay. So if you want to see like other loss functions or optimizers and matrix, okay, so you can check out the corresponding web page, okay, yourself, okay. But the sparse cross entropy basically refers to one-hot vector, okay. So what is one-hot vector? Okay, so there are two ways to encode categorical data. When I say categorical data, I mean like the data are classified into classes. Okay, so the first one is it's an integer encoding. Okay, so for example, if you want to classify color into maybe you have three colors: red, green, and blue. Then you can specify red to be 1, green to be 2, and blue to be 3. So this is like the integer encoding. So each unique category value is assigned an integer value. Okay. But the issue with this integer encoding is that, okay, this using such encoding will allow the model to assume a natural ordering, okay, between categories. For example, okay, you assume, okay, red is smaller than green, which is smaller than blue. Okay, obviously this is not the case, right? I mean, red, green, and green and blue, they do not have like a specific order, right? Yeah, they just represent different colors, right? So, to make it worse, okay, it actually gives like the model certain implication that, I mean, for example, you add up red and green, you get blue, because red is 1, green is 2, 1 plus 2 is 3, right? But this is obviously again not the case. Okay, these numbers just represent the color. Okay, but when you train a model, it may provide such a wrong implication, which will result in poor performance or unexpected result. So instead, we can, use what we call the one-hot encoder. For example, you can encode red to be 1, 0, 0, green to be 0, 1, 0, blue to be 0, 0, 1. Basically, for n classes, you will have like a vector of n dimension, okay? And for a particular class, I mean, say class K, the k's component of that vector will be 1, and all the other components will be 0. When you encode each category like this, okay, it is called one hot vector, and such encoding, okay, prevent the model from, incorrectly interpretations, okay. Obviously 1, 0, 0 and 0, 1, 0 and 0, 0, 1 in the case that we are discussing here, there's no particular order between them, right? And you cannot say red plus green go to blue either, right? So which is and which is good. And this way, okay, it's what we call sparse categorical sparse categorical. Okay, so we use a sparse categorical closed entropy loss because we have sparse label. For each instance, there is just a target class index from 0 to 9 in this class. Okay, and there is just a the class are exclusive. Okay. Oh, I'm sorry. If we use a sparse categorical, then it's integer encoding. If we use a hard vector, then it's a categorical closed entropy. Okay. So if we are doing binary classification, then as we already mentioned, we normally will use sigmoid, okay, elevation function, and we normally will use a binary closed entropy loss. Okay. So I think I already explained the code. Okay. So then we can call the model.fit. Okay. Here we provide like a the training set. Okay. The X train and the Y train. Y train is the label. X train is the feature. Okay. And we set the epochs to be 30. Okay, and we provide validation data, okay, as well. And we will record the result to the history. Okay, so the following will be like it will output like for these 30 epochs. Okay, so what the loss and accuracy for the training set as well as the validation set will look like. And you can see that, I mean, it's going to get better and better, okay? So, yeah, after 30 epoch, you can see like the accuracy is already, for training set, accuracy is 91.9%. And for validation set, the accuracy is 89.2%. So it's reasonable. It's pretty reasonable. Okay. Yeah. So that's about it. So we have a trend neural network, okay, and you can draw the learning curve. Okay, you can draw a learning curve later on. Okay, we'll explain like what this because we have like the accuracy and the loss for training set and validation set, so we are able to draw a learning curve. Okay, so so obviously the validation loss is slightly lower, it's slightly worse than the training set, which is nature. Okay, it's nature. After we use the training set for training the model, so training set accuracy and loss will be slightly better than the validation sets. Okay, and if your training set are skewed, when I say skewed, I mean like they are biased towards certain classes. Okay, some classes being overrepresented, and some and others underrepresented. So we can use the class weights argument. Okay, when we call the fit method. Okay, which will give a larger weights to underrepresented classes and lower weights to overrepresented classes. Okay, so this help to balance the result. I mean, to balance provide. I mean to fight with the imbalanced data. Okay, when will that? I mean, what do you, I mean? Let me give you an example for that situation to happen. For example, if you want to collect the cost, okay, you want to classify like the cost that that will run over the red light, okay, that will trespass the red light. So when you collect the data from the street, okay, supposedly most of the time, most of the cars will obey the rule, right? They will not, just drive through the red light. Okay, only few cars will do that. Okay, so in the collected data set, obviously, the cars that that run through the red light, okay, this category is going to be underrepresented, right? And you have the cars that obey the rule overrepresented, okay, in your data set. Okay, so that's, but if you want to train a model that can classify the cars that will obey the rule or even just run through the red light, okay, then obviously, I mean, using such a data set, okay, to train a model, will be biased. Okay, so you would like to use this class weight argument to deal with this data imbalance problem. You may ask, if I don't do anything about it, what's going to happen? Okay, well, let's say only 1 out of 100 cars trespass the red light. Okay, then since 99% of the car will obey the rule, right? So when you use such a data set to train a model, okay, your model will not learn anything. It is going to learn, okay, that, I mean, for no matter for what input, I mean, it's just output. Okay, this car is going to obey the rule. Why? Because it knows that because the majority of the cars will obey the rule. So as long as it answers like all the cars obey the rule, okay, it is correct 99% of the time, right? So it has a very high accuracy rate, right? But obviously, this is not what we are looking for. We want our model to learn, the feature of the cars that do not follow the rule, right? So here, okay, the set you can set the class weight argument, okay, to deal with this issue, okay, and You can even set like a per instance weight. So what situation do you need this thing? Okay. Sometimes, I mean, you will outsource your data labeling to like to some people, okay, who will do this labeling for you, and to speed up the labeling process. But unfortunately, I mean, because your lab do not have enough manpower, okay. But if maybe your lab will deal with like only 10% of the data set, and the other 90% of data set will be outsourced to other people to do the label. Okay, so obviously you would trust the people who are in your lab to do the label much better than those who who you outsource the labeling to, right? So you can give like more instance weights to those instances that are labeled by your lab members, and I mean the lower instance weights to the labels that are done by like the outsourced like people. Okay, so this is like this sometimes like you can, I mean, this could happen. Okay, and then as I said, because you we have all these training set and validation set, accuracy and loss collected, so we can we can draw the learning curve. Okay, and this is a few lines of code to draw the learning curve, and you can see we use the history, okay, that we recorded, I mean, when we do the training, okay, and plot it, okay, to be something like this. So remember I told you, okay, for learning curve, okay, there are two types of learning curve, okay. The first one, the x-axis is like is a size of the data. The second type is like the size, the axis represent like a number of epochs. And to be honest, like this one is more commonly seen, okay, where x-axis represent number of epochs, and the y represent like either accuracy or loss. Okay, so you can see like we have accuracy and the variation accuracy. Both are, well, kind of like red lines at the top. And for the loss, okay, where those both the loss and the validation loss, okay, both represent like kind of like blue, okay. So at the bottom, and you can see the accuracy grows and the loss, I mean, are getting lower and lower, which is nice, right? But are we, do we have an overfitting issue or not? Okay, the first thing that comes to our attention is that, okay, you may think like, well, remember I told you, okay, normally the validation loss is normally worse than the training loss. Okay, that's usually the case because the model is trained based on the training set, right? So but here you can see that, okay, the validation loss is actually slightly better than the training loss. Okay, this is validation loss, this is training loss. So how come? Okay, same thing can be said for the accuracy. Okay, the validation accuracy is slightly better than the training set accuracy, especially at the beginning stage. Why is that? It is because, okay, at a time when the validation set is evaluated, the validation loss and the accuracy was evaluated, it is at the end of epoch. But at a time when the training set loss and accuracy was evaluated, it is in the middle of epoch. So in some sense, the training set and the accuracy are, what should I say? When we say, like, for example, like after 5 epochs, the validation set and the validation set actually use exactly the model that is trained for 5 epochs for evaluation. But for the training set, okay, when we get that 5th epoch, like a loss and accuracy, it is actually in between 4th and the 5th one. So in some sense, like you need to take that into consideration and do a little bit of adjustment. So in other words, the more reasonable consideration is that, okay, you should, you know, sort of like how should I say, like shift the validation accuracy and validation loss in this graph about half a unit left. Okay, so that they will represent similar thing. Okay, so this is the first thing I would like to tell you. Okay, the second thing is that, okay, yeah, the validation loss here, it's almost going flat already, right? It looks like it can go a little bit lower, okay, but the training set keep going down. The loss of the training set keep going down. But keep in mind, okay, this is the indication when the overfitting start to occur. Okay, so you may want to train a few more epoch, but it looks like the model has started overfitting. Okay, so this is about the best accuracy that you can get, okay, without overfitting, which is like where is it? Okay, for the validation accuracy is 89%, so which is not too bad, okay, considering we are using a very simple MLP model. Okay, so yeah, so you can see you should be able to reach close to 89% validation accuracy, I mean, which we already have. Okay, so we can also tune certain hyperparameters. Okay, for example, the learning rate, okay, and other stuff such as high optimizers. We are using the stochastic gradient descent here, but there are other optimizers that we could use. Okay, that we are going to discuss in the next chapter. Okay, so all these things can help to improve like a model performance. Okay, but we haven't done that yet. But we keep in mind, okay, all these hyperparameters tuning, okay, that could help your model performance, okay, slightly. Okay, it's not going to have okay, so say like your original model performance is like a 70% accuracy, and you want to jump to 90%. Okay, with just hyperparameter tuning, that's not likely. But with the hyperparameter tuning may help you to improve by maybe like a couple percent, okay, like accuracy improvement. Okay, but we are going to talk about those hyperparameter in tuning later. Okay, and you can use the model evaluate to on the test set to get, you can see, well, the accuracy is 88%, 0.5. So it's reasonable. It's reasonable. Okay. Which is even slightly worse than the validation set. But that's, as I said, this is common because this is the first time you use the test set, right? Okay, we use training set, we use the validation set for I mean during the training process. Okay, not directly, but at least we use the validation set to observe like the performance. But we never use test set. So the last time, okay, I mean it's the only the first time and only the last time we were going to use the test set. I mean to evaluate the model, okay, performance. So this is like the result. So so it's common to get slightly lower performance on the test set than on the validation set, okay, because the hyperparameters are tuned on the validation set, not the test set. Okay, in this example, we really didn't do the hyperparameter tuning, but it's I just want you to know that, okay, the model tuning is based on validation set. Okay, so in any case, the performance of the test set will be slightly worse than the performance of the validation set. That's common. Okay. So so you can use this model to do predictions, something like this. Okay. We use the first three instances in the test set. Okay, and then we do the prediction, and you can see like the result of the percent of the here we show the probability for each class. Remember, we have 10 classes. So the first one, okay, is most likely to be the last class. The second one is most likely to be, well, the third class. The third one is almost certain to be the second class. Okay, but if we want, I mean, because this doesn't show you the name, right? So, okay, so we can, you know, include the name. Okay, with we want to show the which name, which class that those represent. So the first one is ankle boot, the second one is pullover, the third one is trouser. So it's going to be something like this. Okay. So this is like so we are done with like using a sequential API to build like a classifier. Okay, although it's a simple one, but I just want you to show you, okay, how we can do that. So well, I think we are running out of time. So next time we will start. We'll talk about like how we can use the sequential API to build like a regressor. Okay, so I guess that's about it. Any question? So if no question, I mean, I will see you in classroom, okay, next week. Okay? Yeah, thank you. Bye.